Right, so the goal of today's lecture is to visualize and be able to interact with 1 million data points. Right? Previously we've seen these examples, and for the sake of recording, let me show them again. Here is my map that I was not able to quickly interact with and re-render when dragging and zooming. So the trick I used here is to hide my layer of data points while I'm dragging, and that way it was quicker. Here in a different example, I was making software for Swedish municipalities, and here I have 3,500 somewhat bubbles here, and once the map loads and everything loads, I can interact with them. Look how slow it is. See, it is so slow. And then if I start zooming, zooming is slow. And if I start playing, I press play here. That's terrible. Like at this point, you would not perceive the interaction as smooth and your actions as connected to the actual screen output that you have. So then I had to search for better techniques, because obviously computer games can do that. Why can I not do? And then, yeah, that little thing. This is made and rendered with a CPU, while games and highly performant data graphics, they are rendered with graphics card. And what's the difference? This is good at following instructions step after step. It only is able to occupy one thread at a time. JavaScript is famously single-threaded, while GPU is able to divide the screen in parts that are repeating and then execute computation in parallel. Even it can sometimes do parallel computation for all the pixels. And rendering also goes in parallel. When I'm showing this thing, how do I... let's examine what's inside here. I'm opening my inspector in Firefox. You have the same thing in Google Chrome, right? In fact, I think it's better to actually use Google Chrome for these kind of situations, because the developer tools in Google Chrome are quite superior, I would say. I can complain about Google Chrome a lot, because they have removed the possibility to use ad blockers, and I don't really like ads on the internet. So I find my both preference and obligation to get rid of my ads on the internet. But for the developer tools, this is actually quite good and even better. It works better than Firefox. So I press right click and I press inspect on one of my bubbles. And what do I see here? I see a circle. Every circle comes in a group, and every group comes in the other group, but essentially what you have here is a tree of nodes in your DOM. Have you encountered DOM, this abbreviation, before? Document Object Model. This is what web pages are made of. Web pages, they're interesting creation. Do you know how they evolved? The people who first made web pages, they were journalists and layout people who designed layouts for books. So from book layouting, you have your headers, you have your columns, you have your divisions, you have your annotation of where everything goes. People were designing the layouts of books and newspapers for their entire professional careers. And then the web came. The web grew as an extension of newspapers, essentially. Now let's make them digital. So by inheritance, you have your... if I'm able to scroll this up all the way, I can see head and body, and I have my divisions here, have span and so on. So these are like parts of the newspapers. It's the same inspiration, it's the same structure here, the semantic structure of publishing your content. And then a lot of terminology from the newspapers, it went on being used by the web pages as well. Do you know if the part of the page is under the fold? Under the fold means here, so it is possible to see it, but you have to scroll to see the content under the fold. What is the fold? It's the fold of your newspaper. It's when you get the newspaper, you first see the headlines on the very top, and then you unfold it, then you have more. So that under the fold part is where you have cheaper advertisements. And then when you want to purchase banners on a website to create ads that I don't like, you would pay more money for ads above the fold. So that's the terminology. But anyway, by extension of that, people were adding these like nested elements with the semantic structure, semantic logic of showing us web pages as if they were newspapers or books. And the graphics there inherited that structure as well. That means that by writing all these nodes in here, you have to keep track of them, or the computer, the machine, has to keep track of every point in your document object model. They become entities in the software that computer has to keep track of and update, re-render, compute the layout on, and so on. That standard is called SVG, Scalable Vector Graphics. You have encountered SVG before in this course, actually all of you, and the way you encountered that, let me see, how do I show it quickest? Remember you've been doing the data art project when you used the robotic arm to make SVG drawings there. So you've generated the circles or other shapes and cool stuff with code, and then you give it to a robotic arm, and the robotic arm draws those. What is inside here? I'm opening Kate's example. Is it Kate? No, not Kate. It's Sissy. Sissy, that's your example. Okay, cool. What is inside? If I open your SVG file that you sent me, it looks like this. What's inside? And because it's a cool editor, it's called Sublime Text, I can find all the occurrences of the circles. I think I can press G. No, I pressed the wrong button. Like sometimes I'm confused with what to press. Yeah, there. And then I get my multiple cursors. Then I can align all of them like that. And if I organize my document like this, here is how Cissy's circle looks like inside the file. Circle, 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 circle. So every one of these circles has fill defined, of course, because there's no color on the filling the circle. There is the stroke color changes based on some kind of loop. Then there is the width, stroke width, the radius, center X, center Y. This is it. This is all that's needed to represent a circle. The benefit of this is that you can generate that with code, as you did. Then you can open it with a completely different tool, Inkscape. Then you can feed it into the robotic arm, and the robotic arm knows how to make a circle, where it should have the center, and so on. Yeah, so the tool interoperability is a major advantage of this kind of approach. Right? Back to the slides there. But in a different example, let's open Windy. Remember the weather particle animation here. How is this done and why is it so fast? Let's do the same thing as we did with my example. If I start inspecting this, what am I supposed to find? Will I find each particle as a separate element in the document object model? Let's figure out. I have section here at the top. I have, now I don't exactly know which one to go into, but maybe it's this one, maybe? No. Maybe it's this one. Yeah, it's this one. Let me try to delete that. Yeah, okay. The thing disappeared. That means it was that one. See, it's one element. It's called canvas. And class map_lib_regl canvas. So that gives you an idea of what kind of software or what kind of technology it was produced with. It's called regl, and we'll mention that further down the lecture. And then you only have to define the width and height of the canvas, styling a little bit, and that's it. That's one element. So everything else here inside this canvas is computed in some way, and your browser doesn't have access to the specific pixels of it. It just throws all the pixels directly onto the screen. This is why it's fast. And this is why this is how it's done with the GPU. Of course, if you try to give that to your robotic arm, it wouldn't have any idea how to render this or how to follow these paths, because canvas is basically just a bunch of pixels on the screen. Okay? So we'll be talking about these different approaches, and we'll be talking about their advantages and disadvantages, right? So there's no free lunch in that sense. Some approaches are better, others are better in other ways. All right, but why? What do I mean by performance, and why care? Of course, reducing gulf of evaluation. We mentioned that yesterday at the lecture of interactive view transformation. Yeah. Improve the satisfaction of using technology. When I'm trying to interact with this one, and it's slow as hell, as a user, my life is miserable. So I don't want the life of my users to be miserable. That's why I want to care about performance. What do we define as performance when we talk about it? First, animations look smooth. They don't in the example I just was showing. Interactions are immediate. No, there is a lag there. And then quick to load, but that's not always as important. So sometimes you can load the page and show like a little loading spinner, and it takes maybe 5 seconds, maybe 10 seconds. If you give the user feedback that is worth waiting for, then that is okay. Then you're in the app, and then the app itself can be fast, hopefully. How to measure performance? Have you done the waterfall performance analysis? Have you done the charts? No? No? No, no, no. Okay, that's good. Then I can show you how to do that. If I go back to my example here, this is how it looks like. Where is my Google Chrome? There. All right. So there is the tab here. Performance, yeah, that one. And then when let's say I press my time slider here, then I press record. There is a record button. Then while it's recording, I go and I find my play button. I press play. It restarted playing, but that's okay. So it played for a time. Now I stop recording here. Then I can expand this view, hopefully. It's nicer when you have like multiple screens set up, and when you can really have a lot of screen real estate to examine these things. But this is what I get. I get the CPU amount of loading, so how much CPU is working. I get the purple part, that means the rendering, so how much does it take time to render the updates on the screen. And then I have some screenshots here, so here I can also track when different things happen as it rolls on and takes the screenshots. And here I can zoom in and see what kind of actions are being performed specifically, what functions are called in my software, and how much time do they take to execute. You see how this is periodic, so every one of these columns corresponding to one step of animation sequence that I have in my time slider. And if I zoom in, I can examine what functions take a lot of time. Google Chrome helps me by highlighting that some of them have these red flags here. So these are your big sinks of performance. This is where your time gets sunk when rendering those. So get offset width is a rather expensive function. Then if I zoom in, I can see what it consists of. So the class add classes. So this maybe sets the colors and sets the positions. Selection each, that is D3 working with updating the circle positions. So then I can really just like sit there calmly and dive in and get map opacity. Look, get opacity here. So the getters and setters. And then if I press one of these, I can see where it comes from in my source code. I can see, okay, that function is like the reason why it's so slow. Yeah. So that's the tool that you have at your disposal. And depending on how understandably you name your functions, it becomes sometimes easier to use and sometimes harder to use. Because here, if I name my functions anonymously, see, I just have anonymous here, and that's not very helpful. Do you know the anonymous functions? It's those arrow functions when you don't write the name of the functions before that, yeah? So you recognize in observable when you were writing accessors or you write your reducers. Those are like inline lambda functions, they are anonymous. They appear like this. This is not helpful. But it's like nicer to write them, easier to write, yeah? But when you have selection, join, then draw data. Oh, draw data, nice. So this is something that I actually wrote. This sounds like my language. And if I look where it is, this is the process frame data. Then I can dive in and see what is being done in there. Cool. So that's how you measure it. Now let's see different techniques and tools of how you can make your graphs more performant. So we'll be scoping it down to only web-based data visualizations and interactive data visualizations. Because in my very opinionated worldview, these are the ones that matter. If you make your data visualizations with R, and you produce them on your computer and you share a screenshot of that or a PNG output and you put that in the article, yeah, it works for the article, but it's not involving the user to be interactive, to be a participant inside your data. So I scope it down to web-based and interactive. What are the different ways to make web-based interactive graphics? It's just 3 of them. Yeah, it's not that many. You have SVG, which we just seen and explored, and we've seen how slow it is and why it is slow. We have Canvas, and we have webgl. That's it. It's just 3 ways. And then you have abstraction libraries, because working with either of them 3 things here will be tedious and time-consuming, and you'll find that you do a lot of manual labor to actually work with any of these directly. So you have abstraction libraries like d3.js helps you to provide a user-friendly abstraction on top of SVG, right? The SVG, these circles output, you can imagine how trivial it is to write a piece of program, a piece of software that would use some kind of template, and you write your loop manually, and your output of your program would be just writing these texts, circle, 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 and then in the loop you just change the colors and the positions of them. It would be trivial, but if you have a complex data visualization, then it becomes hard. Then you need an abstraction layer. You need some kind of user-friendly API that would allow you to say, I want 100 circles and their positions should change according to this formula. That's what you did with D3 in this tutorial. And then observable plot is another abstraction on top of D3.js. And that gives you yet another, a more user-friendly approach. That's when you just say, my X is this column in data, my Y is this column in data, off you go, make me a chart. Yeah, so the observable plot, your code would be like this, maybe 5 lines to 10 lines of code. D3.js, your code would be like this, maybe 100 to 150 lines of code, so like an order of magnitude larger. If you do SVG manually, then the same example would take maybe 300 lines or 400 lines. So it's, yeah, it's the abstractions that you want. But then there's abstractions for Canvas and WebGL as well, and for WebGL the abstractions are very interesting. deckgl, we've seen that in Windy, used in Windy, so that's how Windy is made. I have a tool here because I went in. Again, it's maybe, yeah, it's fine here. I made a tool to compare different rendering techniques. So all of them, 4 examples, they made using these 4 different technologies. I vibe coded this last evening, so it's fully AI produced. Yeah, and I can change my dots here from uniform distribution to normal distribution, and I can either decrease. Divide by 10 the number of points, or I multiply by 10 the number of points that I have. With SVG, I have 1,000 of points. They animate smoothly. That's pretty much the limit of SVG graphics on my hardware capable of pulling it off. Yeah, if I do it 10,000 points, see, it's laggy already. Yeah, and if I take that. No, I actually want to see it in Google Chrome because I wanted to show you another tool here. Where is it? Now I need to more tools, and then rendering. In rendering, I can do what was it called? Frame rendering stats. Yeah, that's where I get the FPS. And then more tools, and then I would what was it called? Performance monitor, this one, yeah. So this graph would tell me how much of CPU is occupied, and this thing would tell me the FPS of the view. So 1,000 points, I get like up to 50, 55 FPS. So that's pretty good. And here I can see the bursts of CPU activity when I do that. If I multiply it by 10, I get down to what's like 30, 40 FPS. So that's visibly laggy here. Look, my CPU spikes, they became much larger. If I multiply it by 10 again, so I have 100,000 points. What do I get here? You see? That's not reasonable. Yeah, that's not reasonable to use. So this is pretty much the limitation of SVG. You can't go beyond 10,000 points there. Right. Although, let's look at the trade-offs. So we mentioned tool interoperability. Give it to robotic arm, it knows what to do. Free interactivity, you get interactivity for free. Remember, here I've added, not remember, but just see how I can add mouse pointer interactivity when I highlight different things here. How is that done? And what is actually like, how is it made? This is my entire code I need to write to make my dots pink on hover. Because each of them is like an individual character in the web page, I can attach hover in the CSS, and I do this, and this is just one line that makes them pink. Yeah. How do I make the points? This is the typical D3 code. Here is when I enter. So this is the circle that needs to appear with the new data. When I press that, the new circles go through these procedures and they show up on the screen. Here's the update. So I update center X, center Y, and I do transition duration, durations 600 milliseconds. This is how they would move to their new locations. And then on the exit, I just remove my data points like that. You see how this code is very compact and easy to read and very usable. But this is SVG for you. Yeah. What else? Free interactivity, CSS animations, responsivity handled by the browser. So you get all the niceties of that the web standards provide for you. Accessibility, yeah. So you can send a screen reader to read the web page, and it would read the circles, and it would be able potentially to read where the circles are located and where the clusters are and so on. And then you can do server-side rendering. That's when you have a heavy computation with your SVG output, and you just get the result like this into your web page when the heavy thing is computed by the server. It is slow because everything is rendered on CPU. It is also slow because everything has to be referenced in document object model and kept track of. Next one is Canvas. So with Canvas, what is a canvas? A canvas is basically a block of pixels. Yeah, it's a rectangle of pixels there. What it does is essentially it bypasses document object model, and because then you don't have to keep track of your things on the page. It's faster because of that. Although you're still using CPU to compute the pixels and stamp them onto the page there. And you lose all of these nice things that SVG was giving to you for free. So you lose all of that. And one benefit there is a very simple and understandable API, and you have full control over your pixels. Let's look how Canvas example would look like. We mentioned that SVG broke at about 100,000 data points here. Yeah, so that was its limit. Can Canvas do 100,000? Yeah, much smoother. Yeah, much smoother. Can we do 1 million? We do 1 million. No, it broke, or it's very slow. And if you look at the performance chart, then your CPU is completely occupied when you re-render 1 million points on this one. So we haven't reached the goal of today's lecture yet. We haven't done 1 million points smoothly. Yeah, it's possible. With SVG it wouldn't be possible at all. But yeah, it's not smooth. Yeah. And my interaction on hover is also quite slow here, even with 100,000 points. So, but with 10,000 points, it's super smooth. The FPS is high. How is this made? This is kind of code that you would write to be able to make circles on Canvas. You would write a for loop, and then you would basically append an arc with certain center X, center Y, radius, and so on. And then you would have to redraw everything depending if the circle is hovered or not. Do you know why? With SVG you didn't have to redraw everything when the circle is hovered. You just remember that was just one line of CSS. Here you have to redraw the whole thing, and this is because when you make a circle on Canvas, and then you make another circle that overlaps the first one, what happens here? The first circle doesn't exist here anymore. You have smashed new pixels on top of it, and there is no reference for the first circle to even be here. You just have one layer of pixels. So to be able to then hover the first circle, which was underneath, you have to recompute the whole thing, and you have to make one of them circles pink. when hovering them like that. And when you move your mouse out of that, you have to redraw everything again, and you make your blue circles again back there. Yeah? Fortunately, that all happens very fast, because you're not dealing with them, you just deal with an array of pixels here. But still, it's done with the CPU, and the code is quite verbose. The interactivity becomes this hard. Also, the interactivity is hard here because what are you hovering? I'm hovering my canvas of pixels. I'm not hovering circles. So my canvas finds out here. It finds out my mouse X and mouse Y position, counting from this corner over here. So I get this distance and I get that distance of my mouse pointer, and I can track my mouse pointer like that. But what do I have to do next? Then I have to do Pythagoras theorem 10,000 times. You see why? Yeah? Here is your Pythagoras theorem. Center x of each circle minus mouse squared. Center y of each circle minus y, mouse y squared. And then you have to do, I think it skips the square root of it, because the square root doesn't change the output. But you have to compute the distance from each circle to where your mouse pointer is at. And then figure out which one is the closest. And then you change the color of that one. See how this is not free. It's not ergonomic when you're implementing this. But it gets worse, because we haven't been able yet. And what is the summary here? Yeah, we haven't yet been able to render 1 million points smoothly and have them react to our mouse pointer events and have them animate. Yeah, so 1 million points benchmark is not reached. How to reach 1 million data points? We use webgl. This is when both the rendering and the computing of graphics all moved to graphics card entirely. You lose all of that. Use GPU, it's really fast. You have full control of your pixels and whatever you're drawing. So what's the downside here? Can you anticipate that? Can you guess what's the disadvantage of using webgl? Give me your best guess.
Is it free?
It's free. It's free open standard. This is the disadvantage. Shaders. Have you heard of shaders? A little bit. This is the most voodoo shit of software development. Of all like in engineering, this and radio antennas are the most voodoo shit ever. This is the code you would write to make your things happen on the screen. And shaders remain the coolest and the most unapproachable part of programming, and this is your brain on shaders there. This example in the background is made with this line of code. One line of code, this thing in the background. Twiggle.app is where people, generative artists, they kind of compete who can make the coolest animated art that fits in a tweet, the code. So you have 179 characters of this, and it produces this cool graphic here. And it's fully interactive. So like, if I start messing around with this, I don't remember what I used to do with this time. Okay, 80, yeah. I see I changed the output somehow. 5, maybe, yeah. Cosine, there is a tangent. I don't even know like which, I can't even read this. there is some parameters which I would change, and it would be like visibly different. See, it's this line of code produces this thing, and it animates. What the hell? I was trying to like understand and parse this code and figure out what's going on by like adding some line breaks here to see what the different operations are happening here. There is for, there is this variable, there's this variable, there's this variable. But ultimately, this is some trick that is happening, and I have no idea. That's your disadvantage. I started learning WebGL here in my little observable notebook. I first made a rectangle. So I told ChatGPT to teach me shaders and WebGL. And he's like, okay, for WebGL you have to write shaders. I'm like, what the hell is shaders? And then it's like, okay, these are small programs that are run by graphics card. And how do I write them? Yeah. So there it explains. You write them like this. You have your vertex shader. You have your fragment shader. It's not JavaScript. It's a completely different language that is more resemblant of C. And then you send that to a graphics card, and then graphics card implements and executes that. Here is about I don't remember how many they are. Here is about 138,000 of paintings in the Museum of Modern Art in New York. Each dot is one painting, and they are positioned here by how large they are, on this large and this large. Yeah, and then I have like a view of all the paintings, and it's 100 and something thousand data points, and it's smooth, it's interactive. Yeah, so I get to change the blending techniques. I can have it look like a little galaxy here. And now you may find some resemblance with the universe visualization that we've seen yesterday. So this is done with these shaders things. And then you have abstractions of them with like software like Unity, where you can make computer games and so on. But once you get into this kind of stuff, you find that Unity may give you a useful abstraction to make your like a character, and make some animations and so on. But then you want to make some custom visual effect, and then that's when you have to go into the shaders and do it manually yourself. Let's watch this 100 seconds of learning WebGL. I hope it is connected to screen. Sound. No. I hope I can connect it quickly.
Web Graphics Library is a JavaScript API for implementing interactive 2D and 3D vector graphics in the browser. It allows developers to run hardware-accelerated graphics with the client's GPU directly inside an HTML canvas without the need for external plugins. It opens the door to 3D web design, interactive games, data viz, physics simulations, and most importantly, beautiful artwork. WebGL is used to render graphics in everyday tools like Google Maps and by the Unity engine to make web-based games. To understand how it works, it helps to first understand basic 3D theory and the rendering pipeline. In a 3D scene, every point is a vertex identified by its x, y, and z coordinates. The vertices are then connected together to form a bunch of little triangles known as primitives. Then a light source bounces off of them to create the appearance of shadows and depth perception. They're then rasterized to convert a 3D vector graphic into a projection of a 2D pixel, which tricks our brains into seeing a 3D object on a two-dimensional computer screen. This pipeline can be customized by writing shaders, which are just functions that tell the computer how to draw pixels pixels on the screen. Shading requires the computer to perform a ton of linear algebra or matrix multiplication to render graphics smoothly at 60 FPS. It's often too much for the CPU to handle by itself, which is why we have GPUs to distribute the calculations more efficiently. WebGL allows us to process graphics on the GPU and is based on a library that's been around since 1992 called OpenGL. To get started, you just need to grab an HTML canvas in the DOM, then get its WebGL context to start drawing. The main program code is written in JavaScript, but shaders are written in the OpenGL ES shading language. A shader will take information about a vertex or fragment and use the GPU to calculate the data required to render it as a pixel on the screen. Luckily, you don't need to write shaders by hand to start adding 3D graphics to your website. You can use libraries like d3.js or tools like Spline to quickly design 3D experiences without much underlying knowledge of WebGL. Stay tuned for a full 3.js tutorial. Make sure to hit the like button. Thanks for watching, and I will see you in the next one.
Cool, right? It's cool and it's hard. Here in my example with data points, let's switch to WebGL. And let's multiply by points. 10,000, 100,000, 1 million. Hey! Look how fast that shit is. It's animated. I can have my hovering. I think there's so much occlusion here, but I can still have my hovering happening on 1 million data points. And this is how my program looks like. Or Claude wrote this, to be fair, but it's not much I can understand from this, being like new to shaders, and I'm coming from d3.js background, but this is, yeah, some voodoo stuff happening. And then the interactivity, of course, is also quite hard. Yeah, I don't even know what it's still a nearest neighbor loop. Yeah, okay. So it's still your Pythagoras theorem that needs to happen there as well. Yeah, here is the Pythagoras formula with the right triangle. Yeah, so same thing. You don't get interactivity for free, but it's really fast. And when I switch between different visualizations, back to maybe 100,000 points, my CPU is barely occupied in this one. It's not even like doing much. The yellow spikes there. So yeah, pretty amazing with this technology. What are the downsides? So when you okay, where is it? The downsides, apart from it being very hard to approach, is that it's hard to actually implement things. And when you work with pixels directly instead of document object model instead of DOM, these are the kind of bugs that you get. So in my software, which I was demonstrating here, I had to implement pressing this one and then dragging the label of this thing, which was not in the library that I've been using. It's not part of that library natively. So I had to, or my colleague at that time, had to write some shaders. And this is kind of bugs that you get. So your pixels become mumbo jumbo because you haven't made pixels and vertices and the fragments and whatnot correctly with these voodoo technologies. And sometimes my label, if it's correctly rendered, by then it floats under this line that connects the trails of the bubbles. So these like pixel level bugs become your bugs now. Before, when you were working with SVG and DOM, you care until the level of circles and until the level of texts and the primitives on the screen. You don't care about pixels. If there is a pixel bug, it's not your bug, it's someone else's bug, right? But now it's your bug here. So then let's look at the abstractions that allow us to not write the voodoo code for the shaders ourselves, but make it quite approachable. Use free and open source techniques. So if I go back to my tool here, I have one implemented in deckgl. It is fast up to 100,000 points. It is a bit slower with 1 million points, although, see, interactivity works, animation, no, it's 1 million, still good. deckgl. This is the code that's needed to make that example. You can see how I define get position function for the circles here, get radius, what is radius unit in pixels, get fill color, that depends on the hover ID, pickable true, transitions, here is my transitions in get position there. So I write the code instead of being the shader code, I write something declarative that is quite readable and approachable for a human, or a human like me. And here is the interactivity example, get fill color based on hover ID. Basically that's it, it's very compact. So we are now back again to like hundreds of lines instead of like 500s or thousands of lines of code, and it's fast. So, yeah, abstract libraries that help you to handle webgl is the way. Let's see some examples of what's possible to do with these abstract libraries. This one shows food insecurity score in different counties in the United States. Do you know who made that? My students in the design class made that. Not programmers. This is their work. It was one of their group projects. It looks like this, and that the example that I was showing you, it looks like this here, running in observable. And I can apply some filters here to show only some of the bars so that they're not occluded so much in here. Yeah. And that's the code. That's the code that was needed to produce this output above here. So you can use that from the slides as a tutorial, so how to use that. Here's a 3.js example, also made by another group of my students, also in the design class. Here is the project Music Galaxy, and it's showing you the graph of different songs that are connected between the different genres, yeah, from data from Spotify. And I can pull different nodes, I can drag them around. This is like a physics computation that makes it possible. But the rendering is done with something, this is the entire code that does that. Rendering is done with something that's called 3D.js. So 3.js is your library for 3D interactive graphics for the web. And then we have seen that example before with soldiers who died in Ukraine from the Russian side. The counter data is collected by Mediazona, the news outlet. Look how fast it is. Every face here is a data point. I can zoom in and out. I can switch to the map here, where they're coming from. I get all the data points distributed across the country and where the people come from. And I can zoom in, and those are still the actual faces, the portraits of the soldiers. How fast is that? How cool is, like, aside from the content itself and it being tragic and questionable in the first place, we can also appreciate the software that's running this and making this data visualization possible. How is it made? Let's inspect. And when we inspect, we see deckgl overlay in one canvas element on the screen here. So that's done as well with deckgl. And I can show you one more example that's made with deckgl. You can guess what that will be. It is this thing, which is now a completely rebuilt. Oh, it takes so much time to load still. It's still ways to improve this, yeah? Always ways to improve this. But this is now a lot smoother. I can zoom in, and this gets filtered by whatever bubbles are available here on the screen. And I can zoom, yeah, and I can drag my time slider and it's fast, yeah? 3,000, 6,000 data points in here. So, new version, hooray. Thanks to my, that other guy who this lecture was initially developed by, Johnny Hort from Synvinkel, who is my competitor in this kind of tools. So he made that example, but his own version, stats map, with a different customer. This is how his example looks like, and I can switch to Stockholm's land bubbles here. They're quite fast. So he kind of ripped off my software and made a clone doing the same thing, but he was doing it so much faster and better. And then I was like trying to figure out how he made it. Then I met him. Then I ripped off his technology that was in his example in here, and then I applied it to my software. And now we meet about every month, and we exchange the ideas and technologies, and I'm learning a lot of stuff from him. So thanks, Johnny Hort, for this lecture and the outline of it. And finally, the drawbacks of abstractions. So this looks cool. Is there any drawbacks of using them? Because it's free and open source, right? So the drawbacks is nothing like one size fits all. And the problem there is that these tools, they shield you from hard stuff, like writing shaders, by providing the abstraction. But sometimes this is helpful, sometimes it is not helpful. So when someone developed these abstraction things for you, and you start using them for your project, and then you find that you have to do some custom stuff in your software, you find that you're not able to, and then you have to resort to shaders, and you have to resort to the hard stuff anyway. Here is the example from this thing. Like outside of the actual rendering of the thing, I had to define the container, and I had to define orthographic view, and I had to write zoom, min zoom, max zoom. Do you know why? It is because this thing, deckgl, it is made by a company called Uber, and they do like taxi, you know. You call taxi from your phone, and they wrote this open source software for themselves to make these beautiful maps on the phone where you have like 3D buildings and stuff. So they made deckgl primarily for maps. As a result, this is a map, faked, and I have to define orthographic projection for the map. What is an orthographic projection? You have a projection surface, you project the Earth like this. You define zoom. Of course, it's nice that you get zoom for free, but also it's in whether you want it or not, the zoom features, because it's made out of a map, even though it doesn't look like a map. So these are the abstractions that I'm stuck with, and the question is, do I want to be stuck in these abstractions? Do I then prefer to use some other technologies, especially if I'm then forced to stuck in someone else's abstraction, which I didn't written or implemented? So these are all the like questions for you to answer before you pick a tool. Here are some tools for making data graphics, and I've put Mapbox Studio here, data wrapper, observable plot, highly flexible on the Y. Harder to learn on the X. So if you use something like Tableau, it's very easy to learn, it's not so flexible. You can use Google Sheets, you can use Excel, right? You'll be right here. If you use D3, it's very flexible, but also hard to learn, right here. If you use WebGL with custom shaders, you're all the way out there. Yeah, so this is some overview comparison. deckgl makes it easier, it provides the abstraction, easier to learn, and it's quite flexible, yeah? And there's ways to also escape the abstraction of deckgl and still write custom shaders when you need to. Finally, the questions are, if I show more data points, on my data visualization? Do I get more understanding from my users? Is it helpful in understanding the world? Is it helpful in understanding the data? Is it eventually helpful in improving the world or inspiring people or doing the important things that we should be doing? Yeah? Case by case, not always. You'd have to run some user testing perhaps and do your research with the users and what their tasks are and how are they succeeding to complete their tasks with more data points that you show on the graph, or maybe aggregated view that you're showing to them. So you may now recognize your pizza assignment where you can show the entirety of 20,000 data points on a graph, and the challenge is to make it somehow understandable. Or you show some kind of aggregations. Here's my orders from California, here's my orders from Nevada. I only show you 2 bars, and maybe you're easy to understand, and maybe it's not so easy to see the nuance in the data because of that. Because there's like different sizes and different flavors that are offered more or less throughout the year, and you don't see that behind the aggregations that you're showing. More data points equals more trust. Here I would answer yes, because by showing more of them low-level data points to the user, you build a relationship between the user and the data source itself. So the fewer aggregations you do and more down to the original data collection process that you're displaying, the more trustworthy it is, yeah? The more the user can have a relationship with the actual data points that you have there. That's it. Do you have any questions?